Last time, we met the tensor from a distance. We said it's the one data type that runs through everything PyTorch does, and we promised we'd build up to our own tiny language model out of nothing but tensors and the operations on them. Today, we stop pointing at it from across the room. Today, we hold it in our hands because once you can create a tensor, read its shape, change its shape, and reach in to pull out exactly the piece you want, honestly, you've already got half of deep learning. So what is a tensor really? Start at the bottom. A single number, then a temperature, a price, a loss value, that's a scalar. 0 dimensions, line a bunch of scalars up and you get a vector. One axis like a row of values. Stack vectors and you get a matrix. Two axes, rows and columns, a grid. And stack matrices, you get a 3D tensor, a cube of numbers. A tensor is just this idea, taken as far as you like. A grid of numbers with however many axes you need. Scalar, vector, matrix, cube. Same animal, more dimensions. And here's the thing that took me embarrassingly long to internalize. In PyTorch, the shape is everything. When you print a tensor and PyTorch tells you size 2 by 3, it's handing you the single most important fact about that object. 2 rows, 3 columns. That little list of numbers is the tag that decides what fits with what. 9 out of 10 bugs you'll ever hit in this course are shape mismatches. Learn to read the shape first, always, and most of those bugs never get a chance to bite you. Right next to the shape lives the dtype, the data type of every element inside. Float 32 is the workhorse, 32-bit floating point, the type your model's weights and activations live in, because gradients need decimals to flow. Int 64 is for whole numbers, counts, and crucially, token IDs, which is how text gets into the model later. And bool, true and false, for masks, which will lean on hard when we build attention. The same numbers can be stored as different types, and mixing them is a classic faceplant. Models live in float. Remember that. Now, reshaping. You've got 6 numbers in a 2 by 3 grid, and you want them in a 3 by 2 grid instead. Two tools do this, reshape and view. Same 6 numbers, same order, just a different window onto them. The difference? View is the fast one. It doesn't copy anything, it just reinterprets the memory that's already there. But view is picky. It only works when the tensor's memory is contiguous, laid out in one clean, unbroken block. Reshape is the relaxed one. It'll give you a view if it can, and quietly copy if it has to. My rule, reach for reshape, unless you have a reason not to. 2 more shape tools you'll use constantly, unsqueeze and squeeze. Unsqueeze adds a new axis of length 1. It turns a flat vector of 3 into a 1 by 3, or a 3 by 1, depending where you put it. Why would you want a pointless length 1 axis? Because PyTorch matches shapes by lining up axes, and sometimes you need to insert a placeholder, so 2 tensors line up and the math is allowed to happen. Squeeze does the reverse. It strips out the length 1 axis you don't need anymore. Add a dimension, remove a dimension. You'll do this in your sleep by episode 10. And finally, reaching in, indexing and slicing. Square brackets get you a single element, row 1, column 2. But the real power move is the colon. It means all of this axis. So x colon 0 reads as every row, but only column 0. That's how you grab an entire column. Flip it, x1 colons, row 1, all columns, and you've got a whole row. And you can take a rectangle out of the middle, rows here to there, columns here to there, and you've carved out a sub-block. That mental model, colon for the axis you keep whole, a number for the axis you pin down, is worth more than any single function in this whole episode. Okay, let's open tensors.py and run all of that through real code. It's short, 2 pages, and by the end, every single thing we just talked about is something you've watched happen on screen. We start by making tensors, then we read their tags, then we reshape, then we reach in. Nothing fancy yet, just fluency. Up top, the imports and the handful of ways to make a tensor. Torch.tensor wraps a plain Python list. Here, a 2x3 of real values. Then the factories. Zeros and ones fill a shape you ask for, with all zeros or all ones. A range lays down a sequence like Python's range, but as a tensor, and random fills a shape with random numbers drawn from a normal distribution. And that last one is how every model on Earth gets its starting weights. Next, we read the tags. The 3 facts you check on every tensor for the rest of your life. Dot shape gives you that size list. Dot dtype tells you it's float 32. And dot device tells you whether this tensor is living on the CPU or has been moved onto a GPU, which matters enormously once we start training, because two tensors can't do math together if they're on different devices. Then reshaping. We take our 2x3x and call reshape 32, same 6 numbers, new window, and print the new shape to prove it. Right below, view 3, 2 for the same result, with a comment flagging that view needs contiguous memory, while reshape will copy if it must. Our x is contiguous, so view is happy here. Watch the shape go from 2.3 to 3.2 in the terminal. Now unsqueeze and squeeze. We take a flat vector and unsqueeze 0 to bolt a length 1 axis on the front. Shape goes from 3 to 1/3, then squeeze strips it back off. The print statements show the shape growing in axis and losing it again. And the payoff section, indexing and slicing. We pull a single row, then x:0 to pull column 0. And there it is in the terminal, col0 tensor 1 4, exactly the first column of our grid. Then a subblock, a slice of rows crossed with a slice of columns, the magenta rectangle from the animation now in code. And that's the whole vocabulary: create, type, reshape, index. You can now make any tensor, read it, and reach into it without guessing. But a tensor just sitting there is a museum piece. The magic starts when tensors compute together, when a 3x2 meets a 2x5, and PyTorch knows exactly what to do, even when the shapes don't obviously match. That's tensor math and broadcasting, and that's next.